Hello and welcome back to Chapter 2 of the CompTIA Tech Plus Prep course. Today we're going to talk about notations and data types and a little bit about our four basic operations. Let's get to it. Alright, so the very first thing I want to talk about is input, output, processing, and storage. So every computer out there, no matter what it is going to have these four categories. Everything can be classified as an input, an output, a processing method, or even a storaging method. And a lot of times you will actually see this spelled as IPOS. Input, we normally process the data, then we output the data, and then normally we store it for a later time. No matter how simple or complex the computer is, it normally is going to follow these four data states. So keep that in mind. So the first section I want to talk about is input of a computer. This is the act of getting data into the computer. Are we looking at, well, how do we interface with the computer? And a lot of times it's going to be an input device. It doesn't matter if that's a keyboard, a mouse, a microphone, a scanner, a touchscreen, a sensor. All of these devices are considered input devices. They take data from the real world and bring it into the PC itself. And how do you do that? Well, you're going to use an input device. After we have our input devices, we're going to move on to processing. So we're going to take all of that data that we inputted into the computer, and then we're going to then transform it into something meaningful. And so this is what processing is we're going to convert it from raw data into usable data. Now, some examples of this could be calculating the sum of numbers, or sorting a list of names, applying a filter. Heck, even playing a video game, the inputs to the video game is going to be something that needs to be processed so that way we can utilize it. Also, anytime that you're going to convert voice to text or your keyboard strokes to text, all of these need to be processed by the processor in order to make it usable. Once it's usable data, we're going to then present that data in human understandable forms, and then we're going to output it. So it's already been inputted through a keyboard, it's been processed through the processor, and now we're going to output it. Now the output phase can come in many different things. They can go on the monitor itself. It can be printed on paper into the real world. It can come out as audio, like an audio speaker, or through a headphone, or even be projected through a projector onto a screen. Now, all of this data is output, so we need to make sure we can capture said output and utilize it. And 9 times out of 10, we're going to be using it as audio output or visual output. This is where we're going to go. Now, we don't always want our output to be there forever, so a lot of times we're going to need storage. So we're going to need to save this data into instructions that can be accessed later. Now, this data will then be put into a storage device. Now, this allows us to keep the work in our programs and data even if the computers are turned off. Think about your phone. If you turn off your phone, do you lose all the pictures that are on the phone? I hope not. That would be very bad use of storage on our phones because we don't want to lose any data here. So we're going to use hard drives, USB flash drives, random access memory, or even cloud storage that's not located on our physical computer, and store it for a later time. Now remember, most of this data is going to be already gone through the input, the processing, the output stage, and now we're onto the final stage of storing it. Now, it doesn't mean that we can't take this data and process it again. It just means that we are now storing it like a long-term storage memory for a later time. The next thing I want to get into is going to be numbers and notational systems. Now, this is going to be the most math that I'll ever get into in this entire course. So if you haven't gone through a lot of math, don't worry, this is as deep as it goes, okay? Now, we're going to use these numbers of, well, ways that we're going to store our data. Our data needs to be stored some way, shape, form, so we use numerical systems in order to do that. And we're going to talk about 4 main notational systems: decimal, binary, hexadecimal, and octal. These are the 4 types of notational systems that a computer uses. Now the first one is going to be decimal. It's base 10. This is what we all know and love and what we grew up with. You all learned how to count to 10 when you were young, and this is what we learn how to do all of our math based off of, which is a base 10. So for instance, if we take the number 345 for example, we could break it out into a 5, a 4, and a 3. So the 5 was in the ones place, so 10 to the 0 power is 1, so 5 times 1 equals 5. 4 is in the tens place, so we have 110, so 10 to the first is 10, 4 times 10 is 40, and 10 is in the hundreds place. In other words, we have 100, so 10 squared, which is equal to 100. We're going to take 3 times 100 equals 300. Now, if we add these all back up together, we still get the same number, 345. Yay! And that's how decimal functionality works. Now, we all know how decimal works, but how do computers work? Well, computers work in other forms, actually. And the first one that most people know of is what we call binary. Binary is position of 2. So instead of 10, our base is now 2. Now this is how computers talk natively. And so think of it like a light switch. It's either on or off. Okay? There's nothing in between. It's just on or off. Now these are what we like to call zeros or 1. 0 for off, 1 for on. And each digit is called a bit. Now, if we put all of these bits together, we can get numerical values. So if we take a number like 1011 and we try to figure out, well, what is this decimal value? We can convert it if we use 2 base 0. So for instance, the very right number was a 1. So 1 times 2 to the 0 power, which is equal to 1, equals 1. The second number is a 1 as well. So 1 times 2 to the first power, which is 2, equals 2. 0 is in the 4's place, otherwise 2 to the squared, which is 0. And then the last number was in our 8's place, 2 cubed, which is 1 times 8, which is 8. If we add this all together, we get a decimal value of 11. This is how binary is created. And instead of counting 1, 2, 3, 4, 5, 6, 7, 8, 9, and with a base 10, we are now talking in base 2. It is either 0 or 1, nothing in between. The next one I want to talk about is going to be hexadecimal. Hexadecimal is the counting to 16. So instead of 2 or to 10, we're counting to 16. 0 through 9 represent their same values, but now we introduce letters into this. We're going to introduce 10 through 15, and 10 through 15 is going to be represented as A, B, C, D, E, F. And a great example of this, watch the video that's linked after this video here, and I'm going to link to you to a clip from The Martian. The Martian used this inside of Hollywood. It was awesome. It was great to see hexadecimal used in a proper format, and we use this quite often to talk large amount of data in smaller amounts of data. It allows us to, instead of talking with zeros and ones, which would take a long time to talk in a more efficient way. Now, if we look at a hexadecimal example, we'll notice the same thing we've noticed with base 10 and base 2. Hexadecimal looks a little different because now we have A, B, C, D, E, F. They have value, and we can break this apart. So instead of 10 or 2, our base is going to be 16. So our first number is in our ones place. So 3 to the 16th of the 0 power equals 3. So 3 times 1 equals 3. B, remember B stands for 11. And so if we took B and we multiplied it by 16, we would get 176. You see how much bigger of a number we got really quickly without even having very much data? It's crazy, and how efficient hexadecimal can be. Now, the last digit, which is going to be in our 256 spot, which is 16 squared, is going to be 1 times 256. So we get 256. Now, if we add all those numbers together, 1B3 is 475. Now, are you going to do this off the top of your head? Absolutely not. So let me give you a quick example of how I like to do it if I need to do some quick conversions. So if you open up Calculator, you have a whole bunch of different modes. 9 times out of 10, your calculator will probably be open up in standard mode. I'm going to switch it into programmer mode. Now, if I want to convert a number, I could easily convert a number by typing it into the calculator and then clicking in which one of these I want on the left-hand column. For instance, if I wanted to turn 10 into hexadecimal, I can click that, and 10 equals A. But for instance, on this problem here, we had a problem called 1B3, and we wanted to convert it into decimal. I could type it in as hex, bring it over to decimal, and now I've got 435. 9 times out of 10 in the real world, this is what you're going to do, is you're going to use a calculator if you need to do this conversion. But it's also really cool to understand what these numbers are. Now for the CompTIA Tech Plus, are you going to need to convert numbers on the fly? The answer is no. So do not worry about if you can change answers on the fly. But they do want you to know what they are. So if I asked you, what base is hexadecimal, you should be able to answer 16. All right. I'm going to hide that calculator away, and we're going to talk about our last numerical set for the day, and it's going to be octal. Octal is the same thing as hexadecimal, about decimal and binary, except for now we're going to be talking about the power of 8. Think of like an octagon. We're talking about the power of 8. Now, we use this a lot in Unix and Linux environments. So if you wanted to know where this is used a lot, it's used a lot in permissions, okay? And so octal is just the power of 8. So if I took an octal number of 273, try to convert it into decimal, I would do the same calculations as I would do before, come out with 187 on the decimal format, and go through with that. Now, if you want to take some random numbers and convert them, go for it. Take some practice, convert some numbers. And what I like to do is I'll grab a random number like 23. And then I'll say, okay, 23 in decimal equals 23. But what does it equal in hexadecimal? What does it equal in binary? What does it equal in octal? And if you can do that, you're way ahead of the curve, and you'll be fine when it comes to this section of the exam. All right, I'm going to change topics a little bit. Chapter 2 continues on with units of measure and how we deal with our data. Now, the smallest unit of measurement on a computer is going to be called a bit. It is either a 0 or a 1. I like to say, think of it like the light switch, on or off, and this is the smallest form of data on a computer. We normally like to store them in what we like to call bytes, B-Y-T-E, and it's 8 bits. And that's a very important number because 1 byte is easy to for us to put an A or a B or a 1 or a symbol into the computer memory using 8 bits, or otherwise known as 1 byte. Okay, and of course, I always love to bring up a nibble is 4 bits. Now, will you be tested on that on the exam? Most likely not, but I love it as a bit of trivia. If you ever get to have a trivia question asking you what is half a byte, it is 4 bits, or otherwise known as a nibble. Now, as this data grows, we're going to keep growing. Okay, so we've got kilobytes and megabytes and gigabytes and terabytes and petabytes. Everything's just growing and growing and growing and exponentially growing year after year. So as you're going through this, sometimes the Tech Plus may ask you, what is a gigabyte? What is a megabyte? And most of the time when I see it on the exam, they're going to ask you which one is bigger, a terabyte or a megabyte. And if you know which one is bigger, the terabyte, then you will be fine on the exam. You'll notice at the very beginning here, 1 kilobyte equals 1024 bytes. And if you keep going, 10 to the 20, the 30th, the 40th, the 50th, we get all the way up to petabyte, which is a huge number. I don't even know what we're at anymore. We're past the trillions mark, and there's a lot of data that's being stored here. All right, the data types. There's only a few more slides for this one that they want us to understand. Data types is a classification that tells how to interpret data. So what we need to do is we need to cover what a string, a character, a number, an integer, a boolean, and a floating point is. So that way, if you're asked on the exam, true or false is an example of what data type, you can answer correctly that it is a boolean data type. The first data type we're going to cover is going to be a character. A character is just a single letter, number, symbol, or punctuation mark. So think of it like an A, a 1, an @ sign, or a period. These are all characters, and only one of them is a character. Now, if we have more than one character, we will then move on to strings. We now have a sequence of characters. So the word example, the X is a character, but the word example is a string. So think of it like an entire grouping or a sentence of text that is stored as a single string. The next one's going to be some numbers. Now, the first number I like to talk about is always integer. Integer is whole numbers only. They can be positive, negative, or even 0, but they still have to be whole. I can't have 1.5 as an integer. I have to have 1 or a 2. Okay? So think of integers as whole numbers. And a lot of people ask, well, why do I even care if the computer thinks it's a number or a string? Well, the computer cannot do arithmetic on a string, but it can do arithmetic on a number. Okay? So if I say 1 plus 1, the computer is going to say 2. But if it thinks it's a string, 1 plus 1, it's going to look like 11, because all it's going to do is take 1 and smush them together. Okay, so we want to make sure that the computer understands what we want it to be. If we want it to be a number, we have to tell the computer it's a number. Now, if we want to talk about how do we deal with those decimal points, that's where we have floating points. They represent numbers that have any decimal points in there. Okay, they can still be a whole number, like 2, but be aware that a floating point is also a lot more precise, but it takes up a lot more space in memory, because instead of just storing a whole number, it's got to store the whole number including the decimal points, like 3.14159, which is pi. We have booleans. These are logical values. I like to say booleans are on or off, zeros or ones, or true or false. Is the light switch on? True or false? If the light was off, it would be false. Are you older than 21? Yes or no? If you are, that would be true. If you're not older than 21, it would be false. So we use booleans a lot in our systems to understand, well, conditional access statements, and as well as testing if something is actually met or not met. Is that car white or red? Well, if I say, is the car white and it's red, it's going to say false. Now, as we represent data on a computer, remember we're always talking about bits and bytes. We want to make sure that we represent the data properly. And so this is why we take care of data types. We make sure that the data type is set properly in our applications and our scripts as we're writing them, so that way the computer knows how to handle the data. Okay? But there's also going to be what we like to call data types. And if you're a user of a computer, most time you're probably used to seeing this, you just didn't know what it was called. So data types, on the other hand, may have what we call an extension. A .txt, for example, which is human readable text, and will be displayed as it is written. This is how we normally display like books and papers and anything with ASCII code. But you can have a whole bunch of other types of extensions, like images, like JPG or PNG or GIF. And we can translate all those dots, those pixels, into images. Now each pixel is set up to be a color, so once it's stored, it can create the image. We have other types of other types of files like sound, and sound files could be stored as a whole bunch of different things as well. MP3, waves, AAC, and these all represent sounds. So it tells the computer that instead of showing us the data in a textualized format, maybe we digitize it and sample it into an audio wave. We do digital digital to audio modulation. So when we play back, we'll actually hear the sound instead. And then lastly, we've already talked about integers and floats. But remember, the reason why we want a computer to understand that math is it's good for arithmetic. And then the last slide for this chapter is going to be talking about programming instructions. I'm going to tie a YouTube video to this section of the course showing you a father telling his kids, telling them how to make a peanut butter and jelly sandwich. While at first you're going to think this is a little silly to watch, take in mind of this is how a computer thinks. The computer is written at is way lower than human speech. It cannot assume things. It doesn't know anything. So it only can do what we tell it to do in programming instructions. If we don't tell it to do something, it just won't do it. And so we have to be very specific to a computer on how we treat the computer and how it's going to process that data. So watch those videos and go on. All right, this is the end of Chapter 2. I'm going to then move on to Chapter 3, but while I do that, make sure that you go through the quizzes. Make sure you go through the hands-on. Watch those other YouTube videos. Try to understand the purpose and the use of this information, because as you go to the exam for CompTIA, they're going to ask you questions that are going to be a little more scenario-based questions. They may ask you direct technical questions, but sometimes you may have to read between the lines. I will see you for Chapter 3. Have a good one.